Okay, you're gonna have to forgive me for this kind of a streak across my screen. That's the lights in my shop, and not a lot I can do about it. Um, you had a lot of discussion on the forum about this subject, which is a coil with a rotor and the magnet on the rotor going by the coil, and a magnet on the rotor going by an opposition magnet. So what happens if we have a rotation in this direction is, as this magnet approaches the iron in the core, it is attracted, and as it tries to leave, it is also attracted. So you have this radius up the center right here, and this half of that radius, if you look at it like this half of the radius is a negative, or is actually a positive action, and this half is a negative action. And so if the core has a specific width here, then half of that is positive, half of it is negative, or at least to the extent that there's interaction between the magnet on the rotor and the core. Same thing happens down here. As the magnet's coming around, it is in repulsion to the magnet right here, but once it reaches that top dead center point, it's still in repulsion, which actually is a motive force pushing it away in this direction. Once they're lined up like that and it gets just the least little bit past top dead center, it pushes it in that direction. And so you have the same kind of thing. The first half of it is negative, the second half is positive. So if this field is bigger than this field, your positive action, which is half of the field, is greater than the negative here, and you actually get a positive rotation. But let's just talk about very specific things. With no coil in place, no opposition magnet in place, you have a specific RPM that your motor is able to turn this rotor. Now, when you introduce the coil, you're going to lose some RPM. That's just what happens. When you introduce the opposition magnet, if you're able to bring the RPM of the motor back up to what it originally was, or more, because of this motive action, what difference does it make what size this field is, what size that field is? What difference does any of this make? Okay, all that matters is that you've went from this to negative reaction and you brought it back to either equal or a positive reaction taking place between the magnets and the coil and the magnet on the rotor. That's all that you really care about. But there are a couple things you need to understand. I haven't brought this up, but I'm going to bring it up here just for information for people. I've experimented with a bunch of different magnets, different diameters, different lengths. Those things, the diameter of this magnet, because of its interaction with this magnet, makes a big difference on this field. And if you remember, I started out with 2-inch magnets here, went to 1 inch, and I've also experimented with the length of the magnets. I've had different magnets in the 2-inch and the 1-inch. I've had 3/4, I've had a quarter, and I've had magnets up to 2 inches long in here. So I've experimented with a lot of different magnets on these rotors, and I built a lot of rotors at considerable expense, trying to figure out what the best combination for this machine is, and just take that as a word of advice. You're going to have to do a lot of experimenting as you're going to figure this stuff out. The other thing I want to talk to you about is okay, here's your coil, and it's got a bunch of strands on the coil in parallel that are then connected. The end of this one is connected to the beginning of this one, and the end of that one is connected to the beginning of this one. You put them on in parallel and you connect them in series. And what does that do? Okay, we've already talked about that before, but here's something that I haven't brought up that you need to understand. there's a specific reason you do that, and that is to increase the capacitance of the coil. And because the coil has a greater capacitance, as the magnet is approaching the coil, it takes longer to fill it up. So instead of being repulsed way out here, because when the magnet's way out here, instead of being repulsed at that point, the magnet gets all the way to here before the coil produces that field that interacts with the magnet when the coil is under load, and then it shoots it on by. You get actual acceleration under load. But the thing you need to remember about this, that works because you've increased the capacitance of the coil by putting a bunch of strands in parallel and connecting them in series. You've increased the capacitance of the coil. I'm going to say that for the third time. You've increased the capacitance of the coil. What do you think that does to the production of this coil if you increase its capacitance to accept the flux the electricity produced by the flux in the iron core? Okay, I've had coils with 3 strands at 1,000 feet. I've had coils 6 strands long. I've had a 12-strand coil that are each 250 feet. I've had a 24-strand coil that each strand is 125 feet. Every one of those coils has the same amount of wire on the coil, exactly, almost to the inch amount of wire, just different lengths and connected in series. And the output of the coil varies from the 3-strand to the 24-strand. The output of that coil under the exact same conditions, exact same rotor, exact same number of magnets, exact same RPM of the motor, the output of that coil varies because of the way the wires are connected. So that's just something for you guys to understand about what's going on with this stuff if you haven't understood that before. And if you haven't built one of these machines, you need to build one just because of all the things you're going to learn when you do it.